Okay, so finally for number 5, this is one of the more complex problems that you can see here. We're asked a couple of things about a given function. So first, we have the function f of x equals x sine x. And first we're asked, what is the fifth term and the Maclaurin expansion of the function below? So that shouldn't be too difficult because you know the expansion for sine x. So recall that sine x, and instead of writing it in series notation, I'm just going to write out the terms, because we're looking for the fifth term anyway. So remember that sine x is x minus x cubed over 3 factorial plus x to the fifth over 5 factorial. Since we're looking for the fifth term, let's write out 5 terms. So that's 1, 2, 3, 4. We need one more. Alright, so those are the first 5 terms, and of course there's more, of sine x. So if we want x sine x, all we have to do is multiply everything by x. But again, we're only interested in the fifth term, so this one. And if we multiply this by x, let's just go with, say, a sub 5. So the fifth term, then, of x sine x would be x to the 10th over 9 factorial, because we just have our sine x function, but we're multiplying through by x, so we get that. So that, I mean, that's a pretty typical question where you might be asked for maybe much further than 5, and if you are, you might want to go to the series representation and then just plug in the n. So let me just show you how that would have worked real quick. So remember that sine x is this, but in the series notation, it looks like the following. We have negative 1 to the n. So we have x to the 2n plus 1 over 2n plus 1 factorial. So that's our series representation for sine. And the one thing you got to be careful about, the first term is when n equals 0. So if you wanted the fifth term, you would have to plug in n equals 4, not n equals 5. If you plug in n equals 4 to this, you'll get exactly x to the 9 over 9 factorial, and you're supposed to multiply by x. You get this. But let's say we were asked for the 20th. Of course, you're not going to write out 20 terms. But if you wanted the 20th term of sine x, it would be when n equals 19. And you could plug it in and figure that out. So let's get to the second question, which is definitely more difficult here. So it says, what is its 100th derivative in summation form of x sine x? So first of all, since I didn't write it out yet, let me write the actual terms of x sine x. So x sine x is going to be all of these with an extra x. So we're going to have x squared minus x to the 4th over 3 factorial plus x to the 6th over 5 factorial, on and on and on. So again, I just took this and multiplied it by x. So we're looking for its 100th derivative. So here's the thing, is that when we were doing derivatives of power series in section 3 of this review, we were using the series notation and doing the derivative. When you do 100 derivatives, though, it actually is more difficult to do this. It's easier to see it just looking at the terms. So that's what I'm going to get to. So that's why I wrote this out instead of writing it in its series notation, because it's going to be harder to do 100 derivatives trying to keep in mind what this looks like at all times. But here's something you should recognize, is that you have all even powers of x as you continue along that power series. If you take 100 derivatives, anything that has a power of x less than 100 is going to turn into 0. For example, x squared. When you take the first derivative of x squared, you get 2x. When you take the second derivative, you get 2. And when you take the third derivative, you get 0. And then from there on out, its derivative is always going to be 0. So you can only take 2 derivatives of that before you just get 0. So if we want to do 100 derivatives, if there was a term that had x to the 100, that one will have a derivative that's not 0, but everything less than that will have a derivative that is 0. So we are only concerned with the terms of this series starting with x to the 100. So eventually, there's going to be a term that has x to the 100. What's it going to have on the denominator? All these factorials are 1 less than the power because we raised all our initial powers by 1 because of this x. So the question becomes, is the term eventually in this series that has x to the 100 power, is that going to be positive or negative? Now, obviously you don't want to count all the way out to x equals 100 and figure it out, so obviously there's got to be a pattern, right? Well, if you notice, the next term here would be minus x to the 8th over 7 factorial, etc. So you can see that all the x's that have powers that are multiples of 4 are negatives, and the evens that are not multiples of 4 have positives. 100 is a multiple of 4, so that's going to be negative. So let's write out the next couple. So the next one would be plus, we'd have x to the 102 over 101 factorial. Remember now, this is following the same pattern. The powers are just going up by 2, the factorials are going up by 2. Minus x to the 104 over 103 factorial, on and on. So in this series for x sine x, if we're going to take 100 derivatives, everything that came before this term doesn't matter because they're all just going to turn into 0. So now let's think about what happens when we do take 100 derivatives. Well, when we took the first derivative of this, first of all, 99 factorial is a constant number, so it's just going to stay there. If you take the derivative of x to the 100, you just follow the power rule. You bring the 100 down, you would lower the power to 99. There we go. When you take the next derivative, the 100 stays there, you bring the 99 down, you lower the power to 98. On and on and on and on. So if you notice, what's going to happen in front is you're going to start building a factorial. You're going to have 100 times 99 times 98, etc. So when you take 100 derivatives of x to the 100, you're going to have 100 factorial. The x term is actually going to go away because when you take 100 derivatives of x to the 100, that last one turns it into a constant. Similar to when you take 2 derivatives of x squared, you don't have x's anymore. So we get 100 factorial, it's negative, over 99 factorial. So keep in mind, we're only going to have to do this for a couple terms, and then you're going to see a pattern, and that's all that has to happen. So what happens now when you take 100 derivatives of a term where its power is greater than 100? So you would start by going 102, 101, 100, 99. So you think, okay, so I'm going to start putting all these powers in front by doing power rule. So you're going to say, I'm going to have 102 factorial. There's one slight problem with that, which is you're not going to have 102 factorial because you don't go all the way to the end. Here, we went all the way to 1 because we got rid of the x completely. You're going to end up with an x squared term left here because you have 102 to start with. So when you take 100 derivatives, you're still going to have 2. So what that means is, of all the numbers that we put in front, 102, 101, 100, we're going to go all the way down to 3, and then we're not going to do the 2 and the 1 because that is still a power of x. So what you have to do here is you have to say 102 factorial over 2 factorial. In other words, we want the part of 102 factorial that doesn't include the last 2. So if we just divide by the last 2, this means all the numbers from 102 down to 3. We still have the 101 factorial here. So finally, let's just do the last one. And now you can probably start to recognize a pattern here. We're going to get 104 factorial, x to the 4th, over 4 factorial, 103 factorial. Again, let's think about what happened. We moved all the numbers from 104 down to 5 in front by doing derivatives. We didn't get the 4, 3, 2, 1 because there's still powers of x. So we have to divide by the 4, 3, 2, 1 if you're going to write 104 factorial. Basically what I'm getting at is writing 102 factorial over 2 factorial or 104 factorial over 4 factorial is a lot easier than writing 102 ... 3 and stopping. It makes more sense to write it in terms of a factorial. And of course, more terms than that. So let's think about what cancels out, because a lot of this stuff cancels out. 100 factorial over 99 factorial is 100. 102 factorial over 101 factorial is 102. Still have the x squared, still have the 2 factorial. 104 factorial over 103 factorial is just 104. Still have the x to the 4th. Still have the 4 factorial. Now, once we've canceled everything out, this looks like a much nicer series, and we can write this in a series, in a summation form. Alright, so this is our last test in this problem, really, is how can you build a summation form out of a series that you didn't know beforehand? So what you want to do is just consider all the components. Okay, so you want to recognize it's alternating, so we're going to have that. You have this 100, 102, 104, so we have just some integer term that's going up by 2 every time. We have powers of x that are going up by 2 every time. And we have a factorial in the denominator that's going up by 2 every time. So we have to include all these things. So if we're starting at n equals 0, we have an alternating term, so we're going to have -1 to something. You can't just put -1 to the n, because that's not necessarily true. The first term here is negative, meaning that when we plug in n equals 0, our first term, this has to give us a negative answer. So you can see if you put -1 to the n, and n is 0, that would give you positive. So we have to put n plus 1 so that we start with a negative, so it matches. We're going to have this term 100, 102, 104. So this is starting at 100 and going up by 2 every time. So that is 2n plus 100. So you can see, when n equals 0, the first term, we get 100. Perfect. When n equals 1, we get 102. On and on. We have powers of x that are going up by 2 every time, starting with 0. So we have x to the 2n. When n equals 0, we don't have any. When n equals 1, the next term, we have 2, we have 4. Good? And finally, we need even-numbered factorials, starting with 0. Plug in 0 for n, we get 0 factorial, which is 1, so that works out. 2, 4, etc. So here we go. We've determined the series representation for the 100th derivative of x sine x. Now, oftentimes you'll be given a function that you can check because, for example, if you got e to the x, you know that every derivative of e to the x is e to the x, so the 100th derivative of e to the x should surely be e to the x. So if you got a problem like this where it was just e to the x and they wanted you to do it by the series, you would have to do all this work that we did here, but you would expect that you end up with the exact same series as e to the x. So if it's a simple function like that, you should be able to check your work. In this case, can't do that because x sine x, doing 100 derivatives, that would be ridiculous because you'd have to use product rule every time and start to be multiple times. So there's no way you can check this except by doing it by the series. So this is a good example of how in a problem like this, that this method here is really the only efficient way of calculating, maybe not 100, but multiple derivatives. Because, I mean, as soon as you get to the second or third derivative of this function, it's starting to become way too long to do. Whereas, if you did it by the series, you only have to work with polynomials, and you only have to do a couple of terms, and then you can just write it as a series instead. So this is an example of how you would do one of these problems where you have to take lots of derivatives of a function, convert it to a series, and find the pattern.